Hi everybody, welcome back to Chem 121. I see that we are in week 3, and more than that though, I see outside my window that it's a beautiful day and it's already too hot. Like, what? Weren't we just like too cold and had to have the heater on still in like April, and now it's like, where's my AC? That's how it feels here anyway. My apartment has terrible insulation. Hopefully you are in a better and more temperature stable environment. Because we're going to be here for the next 2 hours doing the rest of Chapter 2 and starting Unit 3. What do we have coming up? We have a lab worksheet due. That is due Wednesday? When is Wednesday? 2 days from now. That's due on the 21st. Make sure you get that in by that evening, though that is a soft deadline if you need an extra day to turn it in. The assignment will still be open on Thursday. It closes after that, and you'll get an email, so just be mindful of that. We're going to finish Chapter 2 today, so there will be a quiz for Unit 2 going up online, and you'll have a week to do that, so it looks like that's going to probably be due on the 26th, which will be Monday, week 4. And then Chapter 3 is not that long, so a Chapter 3 quiz will probably be going out on Wednesday as well. So stuff starts to kind of cram together as we get towards the middle of the quarter, and then it does it again at the end, so just be mindful of that. Alright, so without further ado, let's finish up Chapter 2 so we can get on Chapter 3. So this section has to deal with density. Density is just a formula that you will be calculating using 2 components and solving for the third one. But we need to actually talk about the relationship of what density is. So you might have picked up something that was far heavier than it looked for its size. So I don't know if you have ever held like lead shot for a shotgun shell. My family is a bunch of rednecks, so they refilled their own shotgun cartridges, so I know all about this. This tiny little bag of lead that weighs like 75 pounds. You're like, holy crap, that's heavy. Lead is very, very dense. Likewise, if you pick up like a bag full of feathers, like you could pick up like a giant bag of feathers, or maybe like a giant stuffed animal or something like that. And these are all things that are really light. So I have this picture of this Darth Vader balloon here because it's so light that it floats in the air. The hot air inside of it has a lower density than the air around it, and so it wants to float, and it will carry the little basket underneath with it. Now, its volume is very, 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 very large relative to the amount of stuff that's in it, which is not that much. It's just hot air. So we're going to define a term here, and that term is density. Density is the relationship of how much mass something has relative to its volume. So if you have a lot of mass and a tiny volume, you have a high density. If you have very little mass and a large volume, you have a small density. And of course, there is a formula for that, and that formula is on the next slide here. D equals mv. Now, I skipped over something on the previous slide, so we'll go back to that real quick. When you mix two things together, they tend to sort based on their densities. And so what I'm going to actually show you is a video of that premise in action. And we'll go to YouTube and grab it from here. So hold on. Let's find the density column. As I always show this video to everyone every year. And it has the most obnoxious, like, do music from, like, a children's video. And it kind of is a children's video, but this isn't going to help me. There we go. All right, so we're going to stack a bunch of things in this density tower. And yes, you have to listen to the music. I have to, so. We're going to sort all these things, except for the vase, which is going to hold the stuff. And then all of these things, except for the cups, which also hold the stuff. And adult supervision. You can't sort that in terms of density. So all of those things are going to be arranged by density. Here are the liquids that are going to be used. In fact, it even says what they are here. There they go. Now, they're ordered left to right from highest density to lowest density. So the honey is going to go on the bottom. Then the corn syrup is going to go on top of that. Then the maple syrup is going to go on top of that, and so on and so forth. And they're added in such a way such that either things that touch each other are soluble slightly, but won't dissolve very much because they're too viscous. So, like, honey and corn syrup will mix with each other, but you have to do the mixing for them. Or we put insoluble layers together. For example, vegetable oil and water will not mix together. So water comes before the vegetable oil. Rubbing alcohol and water will mix together, so the vegetable oil separates those two apart. Alright, so we're going to put these in the column. Here we go. Go slow! And this takes a long time to do, because if you mix them too much, you make one layer instead of two, and you want a bunch of different layers here. And then what the objects are doing here is that you drop them in, and then they fall to wherever their density is sorted. So all of these liquids have different densities, but the objects themselves also have a density because they are made of stuff. And so they will sink to the appropriate level based on what their density is. So you can see that tomato didn't sink all the way to the bottom there. And there's everything. So you can see that the ping pong ball being filled with air has a very, very low density, so it just gets sorted right to the top there. But the tomato, mostly water with a little bit of extra stuff in there, so its density is almost that of water, and it actually sinks down below the water, but above the dish soap, which is why it's kind of floating at the surface of it there. It's really hard to see the plastic dice, but it sinks between the milk and the maple syrup. Here's the popcorn kernel. Of course, the bolt being made of metal sinks all the way to the bottom. So things sort based on their density in any medium, whether that is liquid or gaseous. Solids, they would still sort by density, but it's a lot harder because it's harder to move stuff through solids. So given enough time, that could happen. if the solids are heated enough and have some mobility. I bit my lip during lunch, so I'm like stopping to drink water because I don't want it to get chapped. So I apologize if I'm like drinking water in the mic or I sound like I have a fat lip, because I do. All right. Now, here's the formula for density again. I'm going to reduce this down to just some terms that we're going to be writing down a lot. So there's our formula. D equals m divided by v. I heard the cat. I don't know where the cat is, though. Oh, well. Okay. She'll probably yell at me again. Now, if you know any two parts of this equation, you can solve for the remaining part. That's just simple algebra. Now, it's not terribly difficult to do the algebra if you're solving for d or m, but a lot of people get caught up on solving for v. So we're going to do a bunch of examples here that do a little bit of all three. The first one we're going to solve for is d, and then the next two I'm not going to actually tell you what to solve for, because part of the challenge is interpreting what you're trying to do. So let's look at an example problem. This is the simplest type of problem I could give you. This problem involves osmium metal. Osmium metal is the most dense material that we have access to, or the most dense, I should say, element. A sample of osmium weighs 26.3 grams and occupies a volume of 1.16 cubic centimeters. What is the density of osmium? So the question is asking us for density. So you're going to have to compute the density using the density formula. And since you want the density, this is the part that you want to solve for. You could also determine that because you could say, oh, well, I know how much it weighs. That's a mass. And I know its volume. That must mean that this is the leftover component, so we're going to solve for. And so what we do is you just plug in the numbers. Oops, I didn't mean to put a decimal there. Now, unlike with dimensional analysis, these units don't cancel out, so the units stick around. And then we just punch the remaining numbers in the calculator, which I had to retrieve. 26.3 divided by 1.16. And I get 22.672, so I got to round that up to 22.7 grams per cubic centimeter. And then finally, I do my check for sig figs. This number is 3 sig figs. This number is 3 sig figs. So my answer will also have 3 sig figs, and so we're good here. Oops. Bonked the mic with my stylus here. There we go. Should be okay. So that's how we do a simple density calculation if I give you mass and volume. In other cases, I might give you mass and density, or I might give you density and volume, and you have to solve for the missing thing by moving the terms around and doing algebra. So, for instance, if you solved this expression, you're trying to get m, then what you need to do is you need to make the equation look like this. M equals something. Well, you could just do that by multiplying both sides times v, right? Because if I were to multiply by v, like this, these v's would cancel out, and then this would now just be on the other side. Now, what if you had to do this problem, where I gave you density and mass, and you had to solve for volume? Well, you had to get v by itself. And the thing that most people try and do is they try and do this. They say, okay, I'm going to divide both sides by m. And then say, well, there's my v, it's all by itself. But what you're actually solving for in that case is 1 over v. So you cannot do this. That's wrong. What you have to do is you have to get v by itself, but it has to be on top of the fraction. So the first step is to, oops, I gotta get the right color here. Multiply both sides by v. So you get this. These cancel. And then, now that you have V on top, you could then get V by itself by dividing both sides by D. So there are some equations that you can run into that are just manipulations of the density equation based on whatever problem you're going to encounter. So on the next slide, I'm going to give you a problem, and you might have to rearrange the equation a little bit so that you could solve for whatever it's asking for. All right, so I'm going to hit clear so that my slide, there's the answer. All right, here's problem number 2. A helium balloon has a volume of 2.5 liters. The density of helium is 0.1786 grams per liter. What's the mass of helium in the balloon? Now, when you're multiplying your numbers together, don't forget to also multiply the units together, because you want to get the units that are left over for the term that you're trying to solve for. So, for example, in this case, you are solving for this, the mass of helium in the balloon. What should the units of that be? Well, you could find that out by multiplying whatever units are left over and canceling anything that should be canceled out. For example, something on top and the bottom. And you'll find that you will get something like that. So, go ahead and try this problem. Type in your answer in the chat when you have the solution, and we'll go over the answers together in about 2 or 3 minutes. See you in a bit. All right, one more minute, we'll go over the answers. All right, so let's do the algebra here. Oops, or I could just throw the pen on the floor. That works too. All right, so the first thing I always do when I do this type of problem is I start with the formula, and then I'm going to check off the things that I have in the expression. So I've got volume of 2.5 liters, so I know the volume. And I know the density, so I'm going to solve for mass. So that means that when I rearrange the expression, I'm going to move v over to this side, multiplying both sides by v, and I will get d times v equals m. So I just need to multiply the mass, or I'm sorry, I need to multiply the volume by the density, or in either order, because multiplication is commutative. You can just do it in any order you want. So I'm going to put it in the order of the terms they have here. So density is 0.1786 grams per liter. I'm going to multiply that by 2.5 liters. Now when I do that, this is divided by liters, and this is liters, so those will cancel. And so I'm going to be left with some number of grams. So we'll punch that in the calculator too. And I get 0.4465, which I'll write all those numbers down for now. But now I got to go do sig figs. I have the wrong pen selected. There we go. This is 4 sig figs because these 4 digits are non-zero. This is 2 sig figs. My answer should have 2 sig figs because 2 is the smaller of the numbers. So that's how many grams of helium should be in the balloon. So a balloon with roughly the size of a 2-liter bottle, a little bit larger, has less than half a gram of helium in it. And that's because helium is just so light. All right. I'm going to give you another problem. Now, this problem has some challenges in it in the sense that the units don't match up with what you're expecting. So here's the problem. A glacier has a mass of 46,720 kilograms. The density of ice is 0.9899 grams per milliliter. What's the volume of the glacier in liters? Now you're going to notice here that this unit and this unit are not the same, and this unit and this unit are not the same. Now, if you multiply 2 units together that don't have the same unit involved, they won't cancel out. Same if you divide them or whatever, right? So be careful with this problem. You're going to need to turn kilograms up here into something else. And you're going to need to turn your answer somehow into liters, but you're going to end up getting milliliters as a result of that. So think about what you want to do with these steps in this problem. Plan out your course of action, and then solve the problem. We'll go over the answer in about 5 minutes for this one, because this one's a little harder. say hi. Hi, meow. Meow. I'm trying to get Maya to say hi. Any questions, let me know. One more minute, we'll go over the answers. All right, so what do we do here? There's a lot of steps involved, so let me clear all this ink out. I'm actually going to go to this page, which shows you nothing because for some reason it didn't load that. All right, so the way that this works, oops, gotta zoom in here. So, same issue as before. We have to solve for one of the terms, and we've already identified that we need to solve for volume. So I'm going to rearrange the equation, and you can go back to the previous slide where I solved for V to see how I did this, but there's my units, or there's my variable set up. So now I'm going to input the mass as shown. So that's the mass of the glacier. I'm going to put a big division bar here real quick. I'm going to divide that by the density, 0.98 grams per milliliter. So we need to do some fiddling with this, don't we? First of all, kilograms and grams won't cancel out. And then second of all, I have a fraction on the bottom of a fraction. So we're going to take care of the fraction on the bottom of a fraction real quick before we do anything else here. And so here's how that works. So you might remember that from algebra, if you have something divided by a fraction, that's the same as if you took the first number on top and multiplied it instead by the reciprocal of the fraction. So the reciprocal of the fraction would be c over 1. And then these ones, they don't really cancel, they're just 1. But you can multiply those things together and get that. Now, why is that important? Because units, you could treat units like numbers. So if I have units on the bottom, it's like I am multiplying by the reciprocal. And so my units can go like this, right? In fact, if I get rid of these, I'm going to put them back in just a second here. Now it's like I have 0.9899 grams per milliliter. So whenever you see a fractional unit on the bottom of an expression, just flip it around so that it looks proper, like this. Now all my units can be lined up in such a way that I could cancel them, but only if my kilograms here and my grams were the same unit, right? So what I'm going to do is I'm going to convert kilograms to grams by multiplying by another conversion factor. So if I do this, this kilogram will cancel out with this kilogram, and then I can just do the same thing that I was doing in the previous sections, turning grams into kilograms and so forth, right? In a kilogram, there are 1,000 grams. So this part up here is how many grams there are, right? And then finally, I could take this gram and cancel that with this gram, and these are the only units that are left. That's a big mess, isn't it? So now what we can do is we can multiply the remaining numbers that are left together. So this number, and this number. We're going to divide that bottom one. And that will be how many milliliters there are in the glacier. 46720 times 10 to the 3 divided by 0.9899. And when I do all that, I get this as my answer. I'm trying to count these. 3, 6, 7. But the problem does not want my answer in milliliters. It wants my answer in liters, doesn't it? So I have to cancel out my milliliters and turn them into liters. So the thing that we did on the top here, we're going to do that one more time. Milliliters 10 to the minus 3 liters. And so I can punch that in the calculator. And we get this volume. 4.720 times 10 to the 4 liters, or 47,200 liters. Now you do have to write it this way because the number of sig figs you should have after you do all this math here. All of these numbers here have 4 sig figs. So your answer should have 4 sig figs. All right, those are the examples of density that I have for you. I'm going to go back to this slide here. I'm going to give you this problem for you to try. There's the homework practice at the bottom. So I'm going to give you this mystery metal. The mass of the metal is 17.30 grams. Its volume is that. What is the mystery metal based on the choices on the bottom? Type in the answer that you get. This is one of the easier types of problems. You're going to definitely have to do some of the harder problems, especially on the quiz, so just keep that in mind. I'll give you 2 minutes to type in the answer into the chat here, and then we'll talk about it and then go on to the next section. One more minute. We'll go over the answers. All right, let's go over the answer here. So, in order to figure out the density, all you have to do is divide mass by volume. Now, you're not going to get a number that's exactly one of these results. You're going to find out. In fact, you get one that's kind of a little bit off of one, but it is definitely closest to one answer. So, which of these is the number closest to? Well, it turns out it's this one right here. It's only 0.2 away from platinum. It's over 10, almost 10 away from palladium, and it's more than 10 away from silver. And iridium is a little bit higher. Oh, excuse me. All right, that's density. Let me know if you have any questions about how to compute the density of a substance. You're going to see a bunch of different types of questions on density on the quiz for Unit 2. Some of them are going to be easy like this. Some of them are going to be hard like the volume with the glacier. Make sure you can do all of the different types of problems. And here's a good set of problems to practice. Where'd my cursor go? I'm using the wrong end of the pen. That's why I can't find it. There it is. All right. Last bit of Unit 2 that we're going to do is temperature, because we're not going to do this heat part because it's not actually in the textbook. It's in my textbook. It's not in yours in the current edition. Oh, Maya wants to say hi. All right. Here you go. Say hi. There you go. Are you happy? Why did I circle the 21.45 grams? Because that's the one that is closest to this metal. So our job is to identify the metal. And if the metal is one of these 4 right here, this is our answer is closest to this one. She just left. She just wanted to say hi. That's all. That's my cat. My cat wants to talk to everybody, especially me. All right. Temperature is kind of just a thing that exists for this class. Like, we're going to work with temperature when we get to gas laws. But for now, really the only thing you need to know about temperature is that there are 3 temperature scales that we care about. Fahrenheit, Celsius, and Kelvin. And of those 3, one of them we don't even care about, and that's Fahrenheit. I'm just mentioning Fahrenheit because we use it all the time. For example, if I look on my phone says, oh, it's 71 degrees outside. That number is in Fahrenheit, because if you say it's 71 degrees to a Canadian or somebody from the UK, excuse me, or virtually someone from virtually anywhere else in the world, really. Like, you tell somebody in Japan, yeah, it was 71 today, they will go, holy shit, 71? That's like almost boiling. Because they use Celsius. To them, this temperature is like 22. So, like, my friend in Canada, all the time he tells me the temperature, and I have to convert it from Celsius to Fahrenheit because my brain works in Fahrenheit, even though I'm a scientist. I'm trying to get used to using Celsius, but it's difficult. Now, what the heck is Kelvin? Kelvin is actually used in calculations, and Kelvin's kind of special. Kelvin and Celsius are actually related to each other in the following way. And I'm going to show you that on a scale here. All right, so if I have the Celsius thermometer like this, and then I have the Kelvin thermometer like this, and we'll put like the alcohol in there. I don't know why it's blue, but that's the color I have. All right. We've defined the temperature scale for Kelvin and Celsius to be the same gradations. And what that means is that for each of these, Oh, I haven't defined what these lines are, so sorry. This is freezing point of water. And this is the boiling point of water. Gotta write that down. That's important. Between those are 100 units. And for Celsius, here's what we do. So we call the freezing point of water 0 Celsius. And the boiling point of water is 100 Celsius. Now for Kelvin, we actually put the 0 point somewhere else. And that 0 point is down here at the bottom. So for Kelvin, 0 is set at a temperature called absolute 0, which is the lowest possible temperature. Now, that might seem kind of weird to think of like, oh, temperature has a minimum? Well, turns out what temperature is the motion of gas particles as they bounce around a container. And so the energy that these have is related to temperature. Now, if I were to stop all the motion so that these molecules were perfectly still, so I'm going to erase all their arrows. If I were to stop the molecules completely, they would have no motion, they would have no energy, and we would also say they have no temperature. They are at absolute 0. So this is important in math because if we're typing in numbers into an equation, we don't want 0 to be a reasonable spot. That ruins our math, and I'll show you that in a second. But the end result is that when I get up to the freezing point of water, the temperature in Kelvin ends up being this. That should be a decimal point, not what looked like a comma there. So 273.145 Kelvin is the freezing point of water. And because there's 100 units here, the boiling point is 373. Because 1 Celsius and 1 Kelvin are the same thing. It's just where have we set 0? So by the same token, down here, absolute 0 for Celsius would be negative 273.145 degrees Celsius. And you don't really need to know that in that temperature. But this is just some information about the temperature scale. Now, the reason that we care about Kelvin at all, again, is because sometimes we're going to be using equations that have temperature in it. And if I were to put in my temperature in degrees Celsius, this equation just becomes 0. Everything multiplies together and you get 0. Even worse, if I were to divide by that, maybe I'm solving for something different. I do this. Now my expression's undefined. You cannot divide by 0. So the issue we run into is we cannot use Celsius for temperature because 0 is a reasonable temperature. In terms of, is it possible to get to it? Yeah, you go outside on a winter day, it's 0, right? So Kelvin is what we use in all calculations. And that's why it exists, really, is we've just chosen a different form of the Celsius scale. We've slid everything down 270 degrees Celsius in terms of where its number should appear on the scale. And then we use the formula to calculate it. And I'm going to show you the formula on the next slide. Now, these formulas are shown here in the following way. And I'm actually going to add this extra digit on here. Now, keep in mind that if you only wanted to do 2 decimal points, you could also just write 0.15. That works fine. if you're looking up this formula online, you may see something that looks like this. Temperature of Celsius times 9 over 5 plus 32. Just be aware that 9 divided by 5 is the same as 1.8. So I've written these formulas with just decimals instead of fractions because it's easier to typeset them. 5 over 9 is the same as divided by 1.8 because 5 over 9 is the reciprocal of 9 over 5. You're not going to really need to convert between Fahrenheit and Celsius that often. Celsius and Kelvin you will have to do on occasion. You do have to do these on the lab worksheet, I believe, but temperature is pretty straightforward, and it talks about that in the lab worksheet anyway. Now, if you are just doing temperature for, like, it is a step to do in the problem that you're working on, just Google the temperature. Type in Google Celsius to Fahrenheit, and then it will give you two fields, and you can just type in whatever number you want wherever you need to. Oh, excuse me. And it will spit out the other number so that you know what the result is. All right. This slide just talks about absolute zero, which we just talked about. We already talked about what absolute zero is. It'll become relevant when we talk about gases later on, but might as well just introduce it to you now. I'm not going to make you convert these temperatures because you could just type them into Google, so I'm going to just put the homework practice up there. And that's all we're going to do for Unit 2. All right, so once you've copied that down, I'm going to quickly scroll past the heat chapter. We're not going to do anything here, but we're going to do... this is just a fun example that the amount of energy in a Snickers bar could heat up gold hotter than the temperature of the sun. But we're not actually going to do these problems, so... Hooray! All right, it says see you next week, but I'm going to see you in about 10 minutes. We're going to move from all of the math crap that we've been doing, and we're going to put the math away until we get back to unit, I think it's 6 or so. We're going to do actual chemistry. So when we come back from the break, we will dive into some basic chemical concepts that we're going to explore in this class. All right, so I'll start the timer. There's a car turning around in the parking lot. Because, of course, there is. And I'll put the satisfactory music back on, and I'll see you in a little bit. Hi everybody, welcome back. Wind down our music here. And we'll open up chapter 3, which should pop up. There it is. Alright. Chapter 3 also has the sort of issue that chapter 2 did, in which case we don't cover the last sections of it. So down here, I'm just going to go, we don't do electron configurations in this class. I used to, I wrote slides for it, and then I learned that other faculty weren't doing it because it just didn't seem super relevant, so I don't cover it in this class. Sorry, I gotta keep drinking water. Feel free to have those notes handy in case you do need to reference it at some point, but I'm not going to cover it in this class because it's very complex for a topic that is entirely just trivia, I think, for operating at this level of chemistry. So we're going to focus on the more important stuff, which is just what is an atom, what is its basic structure, like where are the components, and then how do we write symbols and terms that represent these components in such a way that we can describe various properties and features about that. So that's what we're going to do. We're going to start by describing what an atom looks like in terms of a picture. So in chapter 1, we very briefly mentioned what an atom was, that it was the smallest piece of matter that you could have that you could attribute to an element. Now we're going to look at what parts make up an atom, because there are 3 parts that make up the identity of every element that is out there, and it is the different numbers of these things that affect which element you're looking at. So the first thing we're going to talk about is the nucleus. This is the nucleus in the center. The nucleus is the very, very, very dense portion of the atom, where 99.999% of all the matter is. It's the very center, and it's very, 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 very small. Everything past the nucleus is called the electron cloud. In the electron cloud, the electrons move very, 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 very fast. Like getting close to the speed of light fast. They go very quickly. This picture is totally bogus in terms of the size of the atom. So if I was to make this the nucleus, right here, what I'm circling right there, and I have our Taylor's tape here, so let's see how many. So it's about 1.5 inches in diameter. I would have to multiply that by 5,000 or 52,800 to get where the edge of the electron cloud would actually be. So let's do that. 1.5 times that number. And I'm going to turn it into feet. So if I drew my electron cloud like this, and that's the nucleus, the edge of the electron cloud would be 6,600 feet away, or roughly a mile. So Fred Meyer is about a mile away from me, so the edge of this electron cloud would actually go through my Fred Meyer. I live in Everett, near the south, like next to Boeing, so I'm closer to Boeing than Fred Meyer. But atoms are very, 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 very sparsely populated. Likewise, if I were to make this my electron cloud, I could not draw a dot on there in the center that was small enough. Like, that's too big. That tiny dot that I've drawn is far, far too big. So suffice it to say, most of the atom is just a void. It's just mostly empty space. Only a very teeny, teeny, teeny part of it in the very center, excluding the electrons, which are an even smaller fragment of matter. Most of the matter is in the center, in the nucleus. But the nucleus itself is very, very small. Now, interestingly, why don't you just pass through other matter if you are mostly an empty void? Because you're made of atoms, like all things. So why can't I pass through the chair that I'm sitting on? Well, it turns out that there are forces within the atom that become relevant when you apply those parts to each other. For example, you'll notice that the electrons flying around the outside have this minus symbol on them, and the protons in the middle have a positive symbol on them. That property is called charge. And that charge is applied to various types of particles. So if you're a proton, you have a positive charge, and if you have a negative charge, you're an electron. Neutrons, as shown, don't have a charge in them. They just kind of hang out. They're like nuclear glue. They hold the protons together because things that have the same charges will repel each other. And this actually explains why we don't go flying through anything we sit down on. If you here, like, so let's say here's somebody's hand here. And they are going to press onto, I don't know, a wall. Then what's actually happening is that when you push your hand on the wall, your hand has electrons on the outside of all of its atoms. And the wall has electrons on the outside of all of its atoms. Because you could see the electrons are on the outside, right? And when these contact each other, they go, nope, I don't want you next to me. Repel, repel. And so your electrons get repelled by the electrons of anything else. And this is called the normal force, which you might have heard of in a physics class. This prevents you from passing through matter. Your electrons are repelled by the electrons of the other object, and thus you remain in place. You do not get to occupy the same volume that other matter does. It's entirely because of your electrons. All right. Now, opposite charges attract to each other, which means that this nucleon in the center here with the positive charge, this proton, is going to pull this electron towards it. However, I should draw this a different way. Hold on. We'll do it this way. So this electron wants to get pulled towards this proton. However, the electron is also moving in this sort of trajectory. So it already has a velocity. So the end result is it's going to go around the nucleus, but then it's going to see other electrons and kind of move its path and do all sorts of stuff. And the end result is that it doesn't actually follow a linear path because that's impossible. There's other stuff around it that it's going to repel. So when you see the electrons, let me hide that real quick. When you see these sort of, you can't see it because I drew all over it. When you see these like constrained rings in these drawings, we're going to sort of ignore the fact that they are shown like this because electrons don't live on constrained rings. They're not like planets, that how our planets orbit the sun on an orbit that's very regular. Like we have a year that's a very regular amount of time because it takes exactly the same amount of time to go around the, well, not exactly, but it takes almost exactly the same amount of time to go around the sun each time, because the only influencing force on the Earth and its orbit to any degree of magnitude that matters is that the Earth is being pulled in by the sun and the Earth has its own velocity. So it just goes in a circle. If there was only one electron, it would also do that. But when we have multiple electrons, they get a chaotic path. And so instead of saying the electrons live on these rings, that's why we call this the electron cloud. They just live somewhere in this region. And that region is just the spherical area around the nucleus. That's why it's called the cloud and not the orbit. I believe that there's a typo here. So this is weak nuclear force. This is actually the strong nuclear force. I'm pretty sure. I'll have to look that up. Now, neutrons, what do neutrons do? They don't have a charge, but they end up acting like nuclear glue for the protons, because protons should repel each other. They should push each other apart. And this is actually what happens when you get too many protons in elements, such as like plutonium and stuff like that. There are just so many protons crammed into such a small space that they repel. And that repulsion causes the atoms to fall apart, so they become very radioactive. But neutrons follow a different sort of rule, and over nuclear distances, neutrons hold protons together stronger than those charges can repel. And so putting the neutrons in the center of the atom helps stabilize it. Now, we're not really going to talk about exactly how that works. All you need to know is that atoms can have neutrons, and they do. One exception is the only atom that has one proton in it, and that's hydrogen. Hydrogen doesn't need a neutron to balance it out, but there are hydrogen atoms that have a proton and a neutron. Those exist out there. We're going to talk about that in more detail. Now, whenever I look at an atom, my atom is going to be electrically neutral. And I'm going to highlight these words because this is important. So I'll just highlight the whole thing. Atoms are always electrically neutral. And what that means is that the number of protons and the number of electrons have to balance out. Because if they didn't balance out, they would not be electrically neutral. So if I have this atom right here, it says carbon. I haven't told you why we know that that's carbon yet. Carbon has 6 protons and 6 electrons. And if I were to add those two numbers together, positive 6 and negative 6, to get the charge, I would just get 0. Because I have the same amount of positive as I do negative. Every atom will be like this. They will always have the same number of protons and electrons. Now, does that mean that it's impossible to have a different number of protons and electrons? No. It just means that if you have the same number, by definition, what you are looking at is an atom. If you do not have the same number, then what we get is called an ion. We're going to talk about ions in Chapter 4. That's kind of the whole point of Chapter 4. So ions have different numbers of electrons than protons. They can have more or they can have fewer. Relative to the nucleus, it's easy to remove electrons, but it's very difficult to change the number of protons or neutrons in an atom. You'd have to dig into the nucleus and knock some of them free, but they're all kind of glued together. It'd be like welding a bunch of things together and then trying to separate them apart using your hands. That's very difficult to do because those iron pieces that we welded together are held together by a very strong I don't want to say bonds because we're welding. The welding holds it together really well, and we're just trying to rip it apart. That's very hard. With our tools that we have, trying to dissociate things from the nucleus is very, very difficult. But removing electrons is very easy because electrons are tiny, and all we have to do is overcome the force of attraction to the nucleus. So when we want to make an ion, we will change the number of electrons by either adding electrons in, making it negatively charged, or removing electrons to make it positively charged. Because if I were to remove the number of electrons here, so let's show this. I'm going to take away an electron by going like this. That one's gone. Now I have only -5 charge, so the overall charge on the atom would be positive 6 plus -5 is positive 1. So there would be an overall charge. Likewise, if I added an extra electron in here, hey, there's one more. This is no longer 5. This is now... It was 6 when they're equal, but now it's 7 because I gave it an extra one. And the overall charge now would be 6 plus 7 minus would be -1, or 1 minus. So you can adjust the charge by adjusting the number of electrons. Sometimes matter will do this spontaneously. Other times it does not want to. We're going to go over all the relevant details in Chapter 4. All right, that's the homework practice for the first section. But that's the gist of what an atom looks like. So in the next section, what we're going to do is we're going to start assigning terms and descriptions to things so that we can line all this up with the periodic table. So hopefully you have the link from the first lecture for the periodic table. If you don't, I'm going to go get it right now. So p-table. It stuck properties on the end there, but that's okay. There we go. So there's p-table. So you can click on that. We're going to be talking about a bunch of stuff on the periodic table, so having that handy will be useful to you. So that I can say, oh, go look at the periodic table. Look for element 11. What do you see about it? And then so on and so forth. All right. How do you identify an atom? Atoms are identified by the one number, and that number is the atomic number. So if I have an atom with some number of features in it, I can assign it a number. And the atomic number corresponds to the number of protons the atom has. We chose protons because it's very hard to change the number of protons something has. Therefore, whatever your number is on that corner of the periodic table, now on p-table I think it's just in the, is it in the corner or is it the top? Everything is left center, not left centered, but left aligned anyway, so the atomic number on p-table is in any of those boxes, it's the top left number. The number in the top row. It'll always be an integer. Ignore the rest of the stuff for now other than the symbol, because we're going to come back to the symbol. But however many protons you have, that's going to be your atomic number, and that's going to tell you what atom you're looking at. So if you're looking at an atom with 34 protons in it, congratulations, you have found selenium. There it is. If you find an atom with 50 protons in it, hey, that's tin. Well done. If you find one with 13, that's aluminum. And so on and so forth. So we do this for every single element on the periodic table, all the way up through 118. There's some more examples. In the previous example, we had carbon because we had 6 protons, and I told you that we had 6 protons. That meant that it was carbon, which is why in the picture, and we'll go back to the picture real quick, it's called carbon. Now, you can't see all 6 in the diagram, which is why I listed it right here in this box. And the reason you can't see L6 is because otherwise the picture would become too cluttered. So there are 2 protons, maybe one's buried inside that little, like, cluster, and maybe one's just behind. Now, notice that we're only talking about the number of protons. The number of neutrons can vary depending on how many protons are in there. You may need more or fewer neutrons. Ooh, excuse me. So we're going to get to neutrons a little bit later. For now, we're just going to count possibilities. And that number of neutrons, you can just put whatever number you want there. We're going to call the number of protons the atomic number Z, or Z if you're Canadian like me. It's like the only non-Canadian thing I do is, I don't call it Z. Because it doesn't rhyme with the end of the alphabet song, right? QRSTUV, WXYZ. If you go WXYZ, it just sounds stupid, so. Sorry, Canada, you got one thing wrong. Z is the number of the number of protons. That will always correlate to some atom. So for carbon, Z is 6. For oxygen, Z is 8. For fluorine, Z is 9, and so on and so forth. A, however, is something different. A is what we're going to call the mass number, and the mass number is the number of protons and the number of neutrons added together. And I'm highlighting this one because this is the one that everybody always screws up. Because it's not just the number of neutrons, it is the number of both protons and neutrons added together. And that's why we call it the mass numbers, because the protons and the neutrons make up the mass of the nucleus. If I only included the neutrons, I would not have the entire mass. I would only have the number of neutrons, okay? So be careful when we're using these numbers. Now, remember that the number of protons and electrons are going to be the same if the atom is neutral. So looking at Z for a neutral atom also tells you the number of electrons that are there, which is why our carbon atom in the diagram from before had 6 electrons. It was because it had 6 protons also. Last thing to note is that this mass number A is not the same as the atomic mass. So if I go back here and we look at these numbers right here, oops, I didn't mean to hit that one. This number right here, the atomic mass, is not A. Okay? I'm underlining that. I didn't mean to cross out atomic mass there. That's just an artifact of how close I wrote that. But just be mindful. That is not A on the periodic table. That is something different. A is going to be an integer whole number. All right. Let's talk about how we represent atoms on the periodic table. We're going to use some symbology. And that symbology is going to look like this. First, I have this curly brackets E thing here. What we're going to do is, for any atom that we're going to describe, this is a placeholder. I'm going to get rid of the placeholder, including the brackets, and I'm going to replace it with whatever symbol of the element that I want to look at. So if I was looking at, say, chromium, I would replace curly brackets E, which is Cr. I don't put it in curly brackets itself. It's just that whenever I put E by itself, everybody would leave E in there, and you don't want to do that. You want to replace the whole thing with whatever symbol you're looking at. Okay, so that's step number 1. Replace curly brackets E with whatever symbol it is for the element you're looking at. And you'll have to figure out the element you're looking at based on the context of the clues in the problem, or because it just says chromium. You can just enter the symbol. Once you've replaced curly brackets E with the correct symbol, the next thing you're going to do is you're going to write in Z. Z is the subscript before the atomic symbol. Writing the number before it tells you its atomic number. Now, because the atomic number and the symbol are linked, you're always going to have stuff like this. I'm just looking them up on the periodic table here. These are always linked together, so you can never have 6 in the front as a subscript and write anything other than carbon, because they are the same thing. So you might think it's a little bit redundant, and it is. So sometimes people don't write Z in there. Oh, I said Z. God damn it. Sometimes people don't write Z in there. I'm not trying to hide the fact that I say Z. I never say Z. I'm just... Now I have it on my brain, I guess. The next thing you're going to do is you're going to write the mass number. The mass number is actually important. We are always going to write the mass number if we can. The mass number, again, remember, is protons plus neutrons. And there will be something in the problem to tell you how many protons and how many neutrons there are, so that you can add them together and put it there. And then the last thing you do is celebrate, because that's what all you have to do. That's all you need to put together so that you can write what's known as the isotopic notation symbol. Your textbook calls it, I believe, the complete chemical symbol. A shorthand that I have is ZAE notation, Z-A-E. I don't think anybody else uses that, but I thought it sounded snazzy, so that's my contribution to the chemistry world. If somebody is out there and wants to publish that, the ZAE notation, go right ahead. You can have it free of charge. Let's do an example. We're going to work with carbon again, and we're going to use the same atom that we had in the previous diagrams. So I know that my carbon atom has 6 protons and 6 neutrons, so I need to assign it its atomic number, Z. Z is the number of protons, so that's just this. So I would do this. Whoop, there we go, Z. Now I need to solve for A. A is the number of protons plus neutrons. And so that would be protons right here and neutrons. And so I would have 6 plus 6 is 12. So I would put 12 up there. And there you go. That's the symbol, the isotopic notation symbol for carbon. Specifically, carbon with 6 protons and 6 neutrons. Now, there's another way to represent this in terms of just writing out text. And that would be to do the following. You can write the element's name, then put a dash, and then write A after it. And this is often done in situations where you can't typeset a subscript or a superscript effectively. Also, it tends to be catchier. People will say things like carbon-14, which is used for carbon-14 dating, or iodine-129, or cesium-131, or cobalt-70. Like, these are all just an element with A listed after it. So that's another way that you can use this sort of notation to identify atoms and what their components are. So what I want you to do for these examples here is I want you to try and write the isotopic notation symbol for each of these situations. I've tried to jumble them about so that it's not just, there are 5 protons and 6 neutrons, write the symbol. So puzzle it out. You may have to chat with other people in the chat blog to figure out what some of these are, but feel free to do so. And when you get the answer, try and type in any answers that you can. You could definitely do the bottom ones down there. Just as a hint, all of these are for neutral atoms. All right, go ahead and give this a try. We'll go over the answers in about 5 minutes. See you in a bit. I clicked the wrong thing. That was the density column. We don't need that anymore. How are we doing? Type your answers in the chat if you can. I'll give you one more minute and we'll go over the answers together. All right, let's go over the answers here. After I finish chewing on this grape. I clicked on the wrong thing there, sorry. Yeah, a little bigger so you can see it. All right, so I want an atom of chlorine with 16 neutrons. So first thing I got to do is write down chlorine. So the symbol for chlorine is Cl. That should be a lowercase l. Just make sure that you write that correctly. You don't write Ci or something like that. This is something that I see commonly. There is no such thing as C capital I or capital C capital I. So just be aware of that. C lowercase l. And then I'll look on the periodic table. Chlorine is element number 17. So 17 protons. Oh, it thinks that somebody is putting in code. There we go. So there are 17 protons there. Oops. There we go. And there are 16 neutrons. And remember that these two together make A. So if I add those together, 17 plus 17 plus 16 is 33. So when I write down Z, Z is going to be how many protons chlorine has. So that's 17. And then A is protons plus neutrons, which would be 33. All right, for element number 2, an atom with Z equals 25 and A equals 55. So for number 2 here, I know that Z is 25 and A is 55. So I could just rate those in whatever spot they would go. Now I need to figure out what the symbol is. Well, I know that I have 25 protons, so I'm going to go look up element number 25, and that would be manganese. And again, we'll just indicate this is A, this is Z, and this is our symbol. All right, let's do the same thing for the next one. An atom with the same number of protons and neutrons, and A is 36. So if A is 36, what that means is that the number of protons and the number of neutrons must add up to 36. But we also know that these are the same number, right? Which means that each must contribute a half. So they must be 18 for each. So we'll go look up what element 18 is. First, I'll write in Z. So there's my Z and there's my A. And element 18 is argon. So there's the ZA symbol for the third problem, which is the hardest of the three, I think. Oops, there we go. All right, and then finally answer the following questions. How many protons does silicon have? I'm going to just write those directly on here. Well, if this is the atomic number, there should be 14 protons in silicon. How many neutrons does potassium-39 have? Well, remember that down here is the number of protons, so this is E on the bottom, this is A on the top. So if A is the number of protons plus the number of neutrons, and you can't see any of that because it's going off the screen here. Hold on. We'll just write it over here. So if A is the number of protons plus the number of neutrons, and Z is just the number of protons, how do I solve for the number of neutrons? And the answer is, oh, I'm just going to subtract them, because then these would cancel out, and I would be left with, if I do A minus Z, that's just the number of neutrons. So how many neutrons does potassium-39 have? Well, if it has 19 protons, and the total number of protons plus neutrons is 39, 39 minus 19 is 20, there must be 20 neutrons. And then for the last one, how many electrons does sodium-24 have? The number of electrons will always be equal to the number of protons in a neutral atom, so this is just 11. And we're all set. There you go. If you have any questions about these problems, let me know. Happy to answer them. Now, we only really have 5 minutes left, so I think what I'm going to do is, let's see here. Can I do isotopes in 5 minutes? Let me see how many slides there are for this. No, we're going to do this. We're going to come back to this on, when's the next class? It says up here. Where is it? Wednesday. So that's it for today. We're going to stop here. We'll resume the lecture on isotopes when we come back on Wednesday. So in the meantime, we're going to put quiz number 2 up. In fact, let me just put the announcement up right here. So let's see here. Quiz number 2, due Monday. And then that's in 7 days, so that'll be the 26th. So we'll just add that to the announcements right there. I'm going to go unlock that as soon as I take the stream offline. So that will appear. But I do want to thank everybody for coming out to the lecture. It is a wonderful, beautiful sunny day out there, and there's still a few hours left of it. So your homework for tonight is to go enjoy that. Have a wonderful day, and I will see you on Wednesday. Take care.